Okay, everybody, can you hear me?
Yes.
Okay, that's great. Great. Okay, then let's start. First of all, good evening, everyone. My name is Malak Ajram, and I am the Vice Chair of the LIU IEEE Student Branch, and I'll be hosting today's webinar. In today's webinar, as you may already know, we'll be talking about battery management systems with our speaker, Dr. Sessine Mdawar. So let me introduce him to you. Dr. Sessine Mdawar earned his bachelor's degree from the University of Notre Dame in Lebanon in mechanical engineering, and he earned his master's degree in automotive engineering from the University of Bath in England, and his PhD also from in automotive engineering from the University of Bath in England as well. His PhD research subject revolves around realizing an internet-distributed hardware-in-the-loop for a virtually connected hybrid vehicle. Dr. Sessine also worked for several companies like Porsche, Audi, and Caterpillar. He also worked as a teaching assistant at the University of Bath for 3 years, and he is currently working as a battery management system engineer at AVL. In today's webinar, Dr. Sessine will be talking about several topics that are battery safety and reliability, advancements in battery management systems, hardware in the loop or HIL, and cell embellishment. Before we begin with our webinar, I need to let you guys know that this meeting will be recorded and will be posted on our YouTube channel later on. And Dr. Sessine, I need to let you know that you may use both English and Arabic during your presentation. And I need to let you all know that if you have any questions for Dr. Sessine during the presentation, you may ask away, of course, turn on your mics and ask right away. And if you have any questions for us, you may leave them in the chat box and we'll answer you right away. So I think that's all. So let's begin with our webinar. Dr. Sessine, the screen is yours.
Okay, thank you very much. Thank you for the introduction. Let
You're
me
welcome.
start by sharing my screen. Okay, so can everyone see the screen?
Yes.
Yes.
Okay, good. Okay, so let's start. First of all, thank you for having me. So in this webinar, we're going to be discussing battery management systems. So I previously had a discussion with Ali as well. So as I was introduced, my background is not purely electrical. So I initially had a degree in mechanical engineering, then moved to the UK. And when the opportunity came for me to move into batteries, I took it right away, and now I'm working with batteries. Okay, so let's give a small outline of this webinar. So the webinar is going to be divided into two parts, basically, which is, first of all, part one is going to be a bit more one-sided. So I'm going to be discussing more about basically what I've done during my PhD and my background and my area of expertise, while part two is going to be a bit more interactive. So I'm going to be asking you to do some stuff. We're going to be discussing different battery management system techniques and how we can test them, basically. So in the first part, I'm going to give you a small introduction about myself, my background. Then I'm going to start by discussing hardware in the loop, power hardware in the loop, and internet distributed hardware in the loop. And then what I've done in my PhD, which is realizing a virtually connected hybrid vehicle. Then how this helped me in my position now in battery management systems, and how to test them using hardware in the loop. Okay, so some of my background. So I did my bachelor's in mechanical engineering at Notre Dame University. During my bachelor's as well, I did a minor in engineering management. I realized that being purely an engineer is not just enough. So at some point, you're going to need to manage people, manage projects. So having some knowledge about management was important to me, which this is why I had a minor in engineering management as well. Then had the opportunity to come to England, do my master's in automotive engineering, applied for a fully funded PhD in 2017, and I was lucky to get the funding for my PhD. And the PhD took me about 3.5 to 4 years. Should have been 3 years, but due to COVID, everyone was impacted by this. Just for you guys to know, I'm gonna be speaking mostly in English. If you feel it's too heavy, just let me know. I'll try to slip in some Arabic, or if you feel like, oh, you're not understanding the concepts, the engineering concepts, please let me know, because this is the whole aim of this presentation, basically. Okay, then for my experience, so I did an internship at Porsche, Audi, and Caterpillar. So these are internships that I've done in Lebanon, which is basically not proper engineering positions. It's mostly in Lebanon, we don't have much of engineering in this area, but this is the area that I was interested in. This is the area that I liked, and I thought, doesn't matter, even if I have to be a mechanic, I'm gonna need to visualize whatever designs and then conceptualize everything in my head, try to link the engineering with what I'm seeing, and build the knowledge based on this. I also worked with Cummins generators, so in maintenance. Then moved to the UK, did 3 years. During my PhD, I was teaching at the same time. I did teach several courses in internal combustion engines, control techniques, and several other courses as well. And when I was done, I moved to AVL. I had prior connections with AVL from my PhD, so my university was getting funding about $100 million, and they were buying equipment from AVL, which is test benches for electric motors, batteries, internal combustion engines, vehicle simulators, and all this. So I had some communications with AVL prior to moving to AVL, basically, and I think this helped me in my move to AVL. Okay, so enough about me. Let's start with hardware in the loop. So first, I'm gonna be simplifying what is hardware in the loop for everyone. So hardware in the loop is basically constitutes of three main components, which are the real-time simulator, the hardware under test, and the model running in the background. So these three are crucial for hardware in the loop testing. So this is a small example of what is hardware in the loop, but instead of having people, we'll have machines. So in this case, we have the model running in the background, which is model simulating whatever environment we're in. The hardware under test, which is the hardware that we're planning to test, and basically the real-time simulator. So we're basically tricking whatever hardware we have into thinking that it's in a real life scenario, real life operation scenario, and checking the behavior of this hardware before we actually put it on an actual real life operation. So if I have a battery management system, a controller that is designed to control batteries, before I actually put it on live batteries, I need to check that it's actually safe enough that it doesn't blow up the batteries when I do put it on live batteries. So how we do it using hardware in the loop. Another example, so now we got rid of the DAD simulating the situation. In this case, the real-time simulator will be whatever we're seeing, which is the steering wheel, the seat, the hydraulic seat. The hardware under test is basically the driver, and finally the model is basically whatever game, there's a model of the game simulation going in the background. So now moving to proper hardware, so where we don't have humans anymore involved. Hardware in the loop, as I said, three main components: hardware under test, real-time simulator, and model. And I added another component here, which is the host PC. We'll discuss this in details. So taking into account that we have the controller, so we need to understand how the controller fits in the vehicle. What does it do? What is it connected to? What is expected to be receiving signal? What is expected to be controlling? So understanding the controller and what it is in contact with for us to be able to model this. Okay. Now we know what the actual controller is in contact with, so we convert that into a model, and then we upload this into what's called a real-time simulator. So the model of the vehicle, the model of the battery, the model of whatever the controller is going to be in contact with is going to be running in a real-time simulator. Companies that do design real-time simulator are very limited. So there's one of the most common one is known as DSpace. Don't know if you've heard of it. So there's DSpace, National Instruments, and Texas Instruments. But the one that's most common in Europe is basically DSpace. It's a German company. So for us to be able to upload this into a real-time simulator, we basically need a host PC. So the modeling is usually done in a host PC and then uploaded into the real-time simulator and controlled. The real-time simulator is usually controlled in the host PC. Okay? So what is real-time simulator? Real-time simulator, just for you to, it will be running a model of whatever we're having, but it's capable of running it in real time. This is the whole point of the real-time simulator. So it has very strong processor, very good processor that is capable to run a model in real time. As you know, the more accurate the model, the heavier the model, the less real-time capability it has. The less accurate the model, the more it has real-time capabilities, and it's a give and take, basically. So you need to choose whether you want basically high accuracy, very accurate model, or fast model. And this is always a problem when we're designing this, because the more accurate the model, the better we can test the behavior of the hardware under test. The less accurate, that means some of the functionalities we might not be able to replicate properly. Okay, so now we have the real-time simulator with the model and everything. We can control it, and it's now connected to the hardware under test, which is the BMS that you can see here. So it's basically now the BMS is gonna think, oh, I'm in a real car, and we're gonna be testing all the different functionalities of the software running inside the battery management system. So all the functionalities like contactor control, cell balancing, current withdrawal limits, everything. And I'm going to be discussing all these with you at a later stage of the presentation. Okay. One of the challenges then when realizing hardware in the loop is there are three main challenges basically. One of them is inter-step switching. What is inter-step switching? Like I mentioned, the heavier the model, the more accurate, the slower the model is. So that means if we're running a very good, accurate model, that means I might have a time step that is very large. So assuming I want to run the model to give me data every 1 millisecond, a model that is running at a 1 millisecond time step is gonna need to be less accurate than a model that is giving me data every 100 milliseconds. However, even if it's more accurate, if it's getting data, if it's responding every 100 milliseconds, scenario similar to this one is going to occur where, for example, during these 100 milliseconds, the controller is going to send two separate signals, which are A and B. So if the real-time simulator is only running once at T1, at T2, what's going to happen is it's not going to be able to see point A. Basically, it's going to only be able to see point B. That means it's going to lose its accuracy due to the fact that it's not able to compute fast enough. Are you able to see the mouse just where I'm pointing during in the slide?
Not exactly.
Okay.
Can you please use the laser or something?
Yeah. Okay. Let me check. Now?
Yes, now it's clear.
Yeah. So, like I was saying, assuming the controller is sending data to the real-time simulator, it sends point A and point B data, but the real-time simulator is able to compute at T1 and T2. So seeing that it's only computing at T1 and T2, it's gonna skip completely point A because it has received data at this stage. So for us to avoid losing data, we're gonna need a real-time simulator that is able to compute at much faster rate, which is detecting, to be able to detect all the points that are being sent from the real-time simulator, and this is a challenge on realizing hardware in the loop. Another challenge is between the real-time simulator and the controller. We're gonna have different analog to digital and digital to analog converters, and the sampling time, conversion delay, and quantization of these analog to digital converters need to be taken into account. Finally, we have usually two types of processors in hardware in the loop, which are DSP and FPGAs. Each of them has its benefits. So DSPs are usually much easier to design, much easier to implement, but they are slower. FPGAs are much harder to configure, but they are very, very fast. So give and take. So depending on the application, you're gonna need to choose which type of processor you would want to use for your application. Okay, moving on. So now we've realized hardware in the loop. Hardware in the loop is basically a simulator, real-time simulator connected to a hardware. Now we usually, assuming that we have a hardware that is a bit more powerful than a controller. Let's say we have an engine or an electric motor or an inverter or a battery. All these components, they can be tested using hardware in the loop technique, but these are going to be named, this now testing is going to be named power hardware in the loop. The reason behind this is because we're handling power now. So between a controller and real-time simulator, it's usually low power. As you can see, power exchange is less than 100 watts. Whenever we exceed 100 watts, now we're using power hardware in the loop. So in power hardware in the loop, we're going to be adding another interface between the real-time simulator and the hardware that is being tested. And this power interface, which could be like a dyno or whatever, if it's a battery, it's going to be something that would apply load on the batteries or charge the battery. So whenever we're dealing with loads and power exchange, we're going to need the power interface. Now, having added the power interface into the mix, we have new dynamics that we also need to take into account. So having this new power interface, we're going to need to take into account that there's going to be power loss by the power interface, which we need to compensate in the model. The output impedance of the power conversion between whatever the model is asking and the power interface is able to deliver. We need to understand the dynamic range of the power interface, assuming like we have a dynamometer and we're putting an electric motor on the dynamometer. We need to understand what is the dynamometer speed that it can reach, what torque can it apply on the electric motor, and all that's involved in that. And we have to take into account now that we have a power interface, the delay between what we're asking from the real-time simulator and when it reaches the actual hardware is going to increase. So assuming I have a dynamometer and I'm asking it to apply a load, a physical load on the engine that's about 100 Newton meter or 200 Newton meter. So this is not going to be instantaneous like signal between controllers. It's going to need some time to be implemented, to be converted into a physical output to be applied on the engine. And all this needs to be taken into account. Okay, so basically hardware in the loop has its challenges. The same challenges that we face in hardware in the loop are faced in power hardware in the loop with additional challenges. And then we move to the final one, which is internet distributed hardware in the loop, which will face the same problems that hardware in the loop has, power hardware in the loop has, and adding additional problems, which are the internet communications. So what is internet distributed hardware in the loop? Assuming I want to test a car, I want to test the engine, the battery, the inverter, the controllers, but everything before assembling the whole battery. So instead of bringing the engine, bringing the battery, bringing the electric motor, and assembling everything and then testing it, what if I can test this while the engine is still in one side, designed by the engineers that are trained and professional to design engines, the inverter, same thing, the battery, same thing. And what if we can communicate these hardware to think that they are in a real car, and then we can test the behaviors before we actually do assemble every single component. This will give a much better understanding. So assuming nowadays, expertise are very limited in companies. So companies in the old days, like big car companies, Audi, BMW, Land Rover, all these companies, they used to do everything in-house. Nowadays, the expertise is more distributed. So they have an engine in the car, they have an inverter in the car, they have a battery, and they don't produce everything in-house. They might have a battery designed in Germany, they might have an inverter designed in France, and they might have an engine designed in the UK, for example. But shipping everything to a single place and assembling and then finding out that there's a problem is not cost effective, basically. So we would like to test all these things while they're still on sites, and detecting the problem earlier than before starting the assembly. So this is the idea behind internet distributed hardware in the loop. This is the aim of this type of technology. Okay, so the challenges faced in internet distributed hardware in the loop, like I said, are the same as hardware in the loop, power hardware in the loop, and adding the challenges of the internet communication. So when we're using internet as the communication medium, we have a delay in the communication. We have jitter, which is having unstable delay. So the delay might vary between the day and night, which is not something. So even if we accept the delay, we need this delay to be constant for us to plan accordingly. If the delay is varying, that means this is adding an additional problem. Another problem is packet loss. So if I send you data and you don't receive it, it's being lost in the communication. These parameters are usually dependent on the choice of communication. So yeah, it's getting maybe a bit too technical, but when you're using the internet, there are two communication protocols that we use, which are TCP and UDP. UDP are usually, like for example now, what we're doing is basically we're using UDP as the communication medium. If you lose me for a couple of seconds, the internet is not gonna drop, it's gonna carry on, and you will just have lost couple of seconds of this presentation, but it will carry on. While TCP, on the other hand, will stop everything just to ensure that the packet is being received. So it will, if I send you information, it will be reaching you, then you will be responding to me confirming that this packet is being received. So no new packets will be sent, no new information will be sent over the internet until handshake confirming that the previous information has been received. So a choice between UDP and TCP is crucial for when running internet distributed hardware in the loop, depending on how crucial the information is. If we don't want to lose any information, we use TCP. If we're okay with losing some of the packets, we use this UDP. Having got rid of the communication protocol, we've chosen the communication protocol, we have to determine the round-trip delay, the one-way communication delay, and the delay different times of the day, like I mentioned, the jitter. So during the day, the delay might be higher, during the night, the delay might be lower. Moving on to what I've done in my PhD. So in my PhD, we had to realize a virtually connected hybrid vehicle. So we got funding from the UK government to do this project. The aim was to test the feasibility of assembling a whole car without basically bringing all the components in one place and doing the assembly. So the funding was done by the UK government. It involved about 6 universities. One university had the engine, one university had the battery, one university had the inverter, electric motor, and the controller. So the battery management, not the energy controller, which divides the task between the different components. And for me, I had to do it for the engine as the hardware under test. So I had an engine in my test rig, and I was working on communicating that engine with all the other components over the internet and testing the feasibility of doing this and how accurate the test will be. Okay, so when I was doing this, I had to understand the health setup that I want, the computational capabilities that I need in the DSpace, in the real-time simulator, the power interface, because I am now dealing with power, so the engine is producing power. I will need a dynamometer to absorb that power, and I will need to understand how much delay there is from when I ask the dynamometer to apply load to when it's actually applying load. I need to make sure that the whole power hardware in the loop is stable. You don't want the engine to stall and turn off, or for it to get stuck and reach 10,000 RPMs and blow up, basically. I had to test the internet communication between my university and all the other universities, and I needed to come up with an architecture for the communication between my university and the other universities. And I needed, these are a bit technical, I'll just skip over those. So the architecture that I came up with is basically having a central university that manage all the communication, which is the power management controller site. So all the other components will only communicate with that site and be receiving data and sending data from that site. So it will be monitoring all the information. And this is the network characterization between my university and the others. So this is the delay in the communication between University of Bath and University of Nottingham. So you can see on average, I can send information and it will reach Nottingham University and come back to me in 11.4 milliseconds. With Newcastle University, it's 14.4, Loughborough University, 11.5, Warwick University, 10.8, and UCL, it was 5.2 milliseconds. Oh, good?
Yes.
Yeah, good.
Dr. Sessine, I think someone has to say his hand raised. Rayyan Kiwan.
Yeah, I have presentation mode. I can't see what's happening. Okay, go ahead.
Hello, sir. Thank
Hello.
you for this presentation.
Yeah.
I have a question.
Go ahead.
Now, 5G technology, the latency will be decreased.
Okay. This is... Yeah, go ahead.
So maybe the internet will be faster more than 11.4 milliseconds, or...
Okay. Let me explain to you how internet works. So even the 5G is basically increasing. If you have a pump, the water flowing from one point to another, the speed is limited. However, you can increase the diameter of the pump. So water cannot go from one point to another faster if you increase, maybe this is the wrong example. Basically, internet communication is limited by the speed of light. So when you're sending data from one point to another, you're basically sending light. The speed of light is constant. So if it's 5G or 4G, the time delay is going to be the same. Now the difference is going to be you're going to be able to send more data, but the delay is going to be the same. So this
Okay,
is,
thank you.
yeah. The only difference with 5G is you're gonna be able to send 1 gigabytes, for example, and
More massive data.
sorry.
More massive data.
Yeah, so you'll be able to send bigger amounts, so more data, but the delay is gonna be the same because how internet works is basically it follows the speed of light, and what it's doing, it's sending a light through an Ethernet cable, which is the lower the quality of the Ethernet cable, the slower the internet. The better the quality of the Ethernet cable, the higher the internet, and it will follow basically it's gonna be about 1/3 the speed of light because it's gonna be going through mirrors inside the Ethernet cable. So this is why in Lebanon, sometimes when you call the internet company and they tell you, you tell them the internet speed is very low, they'll ask you بيقولوا لك أي شريط عندك؟ هذا الشريط الأسود اللي عمره 50 سنة بدك تغيره بدك تجيب واحد جديد.
Okay.
Basically, it's the same because it's an old wire. The reflection of the light inside of this wire is gonna be reflected in a bad way, and it's gonna reduce the speed of the internet. Okay?
Okay, thank you.
Yeah, no worries. Okay, let's carry on. Yeah, please, if anyone has any questions, don't be afraid to stop me. I prefer it when there's interactions. Okay. Okay, so in my PhD, basically, I carried on by actually so this is the experiment that I performed. I had the engine. So this is basically the layout that you see here in the sketch is actually what I've done in my PhD. I put an actual engine. I had the power interface, the real-time simulator, and it was sending and receiving data over the internet to test with the other different components that are gonna be part of the hardware in the loop experiment. Okay, enough about hardware in the loop. Let's move on to how is this applicable for battery management systems. So, why do we need hardware in the loop testing for battery management systems? First of all, it's cost effective, so it allows us to start the testing before actually having batteries. So, like now in my work, we still don't have batteries, but we're actually able to test the battery management system because we know the design of the battery, we know what's the number of cells, the layout, everything. We can replicate it in our hill rig, and we can start to test the different battery management system functionalities before actually having or putting it on the real battery. The other thing, it's easy to maintain and run. That means any small modification, I just get up, modify it in the test, new features added, modify it in the hill rig, and this will allow me to test all different types of feature. But on the other hand, if you have the actual hardware that you're testing on, you don't have this flexibility and this easily because you need to be on site to be able to test. While this is done at low voltage, the hardware in the loop process doesn't mean that there's going to be an explosion, doesn't mean that there's going to be a big fire, and you can basically perform the tests while sitting at home, while just controlling over the internet. Reduces damage, like I said, if the software teams comes to me and tell me, okay, this is the battery management system software that we have, I wouldn't, if I was a sane person nowadays, I wouldn't go and put it on actual batteries right away because I don't want to blow up the batteries. I want to ensure that the software is doing what it's designed to do before I actually put it on batteries. So this is why it will limit damage in case there was some design flaw in the battery management system or not. More than this, it will allow testing of extreme operation conditions. So let's say I want to test extreme operation condition. I don't want to actually do it on a battery because, or if I do, I don't want to repeat it several times. I would like maybe to do it once. While if I want to test, if I'm doing it on the hair rig, I can do extreme operation scenarios without actually being afraid that something is gonna blow up or something is gonna be damaged or people are gonna be injured as well. Finally, the reason why now companies are actually doing hardware in the loop is because now it's a new industry standard. So when companies go and say this software is basically follows industry standards, so this is now required by all companies. When they release their software, they have to adhere to specific requirements or specific standards. And now having software being hardware in the loop tested is a requirement basically for the companies to stay relevant. Okay. A lot to take in, bit heavy. I'm gonna give you guys 5 minutes break. During this 5 minutes, it's not gonna be technically a break. So during this 5 minutes, I'm gonna need you to design for me a hair rig for a BMS system. So assume you have the BMS controller and you want to design a hair rig for it. What do you do? Basically, how do you approach it? What are the steps? Okay, you can take 5 minutes. I'll speak back in 5 minutes, basically. Okay. Okay, welcome back everyone. Like I said at the start, this is gonna be more of an interactive process now. So I'd rather you interact with me, give me your feedback, give me your opinions of what we're gonna do next. If you don't feel comfortable in English, we can do it in Arabic, in French, whatever language you're comfortable in, but I'm gonna need you to interact with me a bit, just for me to make sure that you're getting the most out of this presentation, basically. Okay? Okay, let's move on to the next slide. Okay, so I gave you 5 minutes to design a hair rig, basically. Like we said, we have the controller. What do we do with this controller? What should it be connected to?
Real-time simulator.
Actuators or
Real-time
motors.
simulator. Very good. So real-time simulator. So the actuators are usually very good answer as well. So actuators are usually either built in within the real-time simulator or are gonna be added, which is gonna be, this is something that I didn't mention, but it's gonna be at the end. Who did say actuators? Who's the person?
I am.
Oh,
I am.
good. Okay, so the real-time simulator. So we connect basically the BMS to the real-time simulator. Okay, what do we need for this real-time simulator? For us to control this real-time simulator and for it to run, what do we need?
A program coding.
Perfect. So we're gonna need a model of the car and of the battery. So this is gonna be in contact with the real-time simulator, and the real-time simulator is gonna be simulating the batteries and the car. So كأنه يعني راح يكون عم بفكر حاله انه هو in contact with batteries and the car. And this, the real time, the battery is gonna be, the model of the battery and the car is gonna be running inside the real time simulator. Okay? How do we control the real time simulator? With the host PC. So I'm gonna have a host PC that controls the real time simulator. And finally, like Ryan said, we're gonna have actuators. So actuators are not a necessity, but sometimes we might need them. So as you can, if you look at this real-time simulator, it looks a bit limited. So the main aim of this is to actually run the model in real time. So this is usually designed by the company DSpace to be able to run the model in real time. Sometimes it's gonna be, it has some actuators built inside it, but it's not enough. And this is how companies make money, basically. So DSpace will tell you, oh yeah, well, it doesn't do everything, it doesn't have all the actuators. Why don't we sell you an actuator? So in real life, you might need to buy other components from the company that are that will emulate things that you need the controller to be seeing. In this case, you might need to buy. So this simulator that you see here will simulate all the batteries, all the battery pack, the individual batteries. So it will have, like you can see, cell 1, cell 2, cell 3. It will be emulating every single battery. Okay. So now we designed the hardware in the loop for the BMS. Now let us start the testing. So now we're gonna start to test some of the functionalities that are in the BMS. Starting with cell supervisory circuits. Does anyone know what is cell supervisory circuit? Okay. I'm gonna assume then no. So over here, what you can see is a battery module. So a battery pack is usually constituted of several modules. So what you can see here is a battery module. Cell supervisory circuit is a circuit that goes across the battery module and it will be monitoring every individual cell in that module. So it will be a wire, let's say an electrical wire, going across every single battery, and it will be monitoring the voltage of the battery, the current of the battery, and the temperature of the battery. Okay? So this is happening for every single cell that we use in the batteries, in an electric battery. So the BMS is going to be receiving data for every single battery. So imagine the amount of data that the BMS has to deal with. It's going to be receiving data for cell data. It's going to be the voltage of every cell, the current of every cell, and the temperature of every cell. Okay? And it will be also returning the module voltage. So the whole module, what is the voltage of that module? Okay?
Yes.
For us to test this, yeah, go ahead.
No, I didn't have any question.
Okay. So for us, now you're going to ask me, how is this going to be tested in the hardware in the loop? So in the hardware in the loop, we don't have this. We don't have a battery module. But what we do have is what I showed you earlier, is this cell simulator. So a cell simulator will be behaving like whatever cells you'll see in an actual battery. So what I'll do in my hardware in the loop testing, I'll say cell 1, set cell 1 equal to 3 volts, cell 2 equal to 2.9, and cell 3 equal to 2.8, let's say. And what I expect to see in the CSCs is this specific data. So from my end, I have to make sure that the simulator is accurate. It's when I ask it to provide 3 volts, it's actually doing this. And on the other side, I have to make sure that the CSC are actually able to read the correct voltage. Usually, CSCs are designed to be accurate to a specific extent. So let's say plus or minus 20 millivolts. So if I'm asking the simulator to do 3 volts, I should be able to see on the CSCs 3 volts plus or minus 20 volts. If it's outside that range, we go back to the supplier. We say, okay, these CSCs are not working properly. Please provide us with new CSCs, or we have to check if there's a problem with the BMS and the CSCs are actually working fine, but they're not reporting the correct, the BMS is not reading the correct value. And then in this case, I have to go back to the software team who designed the BMS and tell them, you'd have designed something wrong in reading the CSCs, and you need to fix this. So this is one type of test that we can do for CSC testing in hardware in the loop and for battery management systems. Another thing is cell balancing. Has anyone heard of cell balancing in electric cars?
No.
Okay, good. Some interaction, even if you haven't heard of it, it's good for me to know what.
Similar to equalization or not?
Yes, so the whole aim of cell balancing is to make sure that all the cells have the same voltage. So the aim of cell balancing is to ensure that the pack is charging and discharging at the same rate. So assuming we put the car on charge, we don't want one cell to be charged faster than the others, and if we're discharging, we don't want one cell to be discharging faster than the others. So having explained what the CSCs are, this information from the CSCs is going to be sent to the battery management system. If we're charging the car and then we see we have data from the CSC saying cell number 1 while charging, this is now 3.4 volts and this is 3.3 volts. What I want to see from the BMS is control over this cell for it to reduce the voltage by allowing less current to go through it, while more current is going through these so that the voltages match, basically. Same thing when we're discharging. If we're in operation, we don't want one cell to be discharging faster than the others, so we have the cell balancing. This is usually achieved. We will have inside the CSCs, we will have a resistor across every single cell. So if the cell is underloaded, we turn off the resistor, so more current is going through the cell. If the cell is overloaded, we increase the value of the resistor, so more load goes through the resistor and less through the cell. The whole aim of this, we want all the cells to have the same lifespan. So usually, if there's a discrepancy between the cells, that means that there are some cells that are more tired than the others. For cell balancing will allow us to extend the life of these cells by putting more load on the other cells, so that we extend the life of the pack, because the other cells will be healthier basically, and we would like to extend the life of the whole battery pack. Okay?
Yes.
Okay. Another functionality. Has anyone heard of auxiliary battery? So this auxiliary battery is usually also used in internal combustion engine cars. What is the auxiliary battery? What is common between electric cars and internal combustion engine cars, you think? Which battery will be common? Okay, let me explain. Yeah, Hanan?
Yes, the auxiliary battery is common between them. It's
the internal combustion engine car and the electric car. So now in internal combustion engine cars, we have batteries. What are those batteries?
To turn on the car.
Perfect. So it's just a 12-volt battery. It's used to turn on the car. It's used to control some of the small features. What was surprising to me, and what I think is going to be surprising to you, that these same batteries are also used in electric cars. So recently on the news here in the UK, several reporters are going on the television saying, oh, people will go park their cars in the airport for 2 weeks, they come back, and then the battery is empty, and they cannot drive home. So automatically you would think this is the 400-volt battery, which is empty. It turns out there's another battery, which is the 12-volt battery in the car. And this 12-volt battery is used to start the car. So we don't want the 400-volt battery to be connected all the time. So what they have is a 12-volt battery. And if this 12-volt battery is depleted or foggy, basically, it's empty, you cannot start the car. The reason is I'm going to explain this now. So usually, this is an electric circuit that you're going to be seeing in an electric car, where you have the 400-volt battery pack. So assuming we have a 400-volt battery pack here, and on this side you have all the auxiliary, the inverter, the electric motor, everything that you see inside the car, the heater, everything. Usually, when the car is parked, these two contactors are opened. Okay? Now, for us to start the car, we need to close these contactors. So to allow this battery to be connected to the whole circuit. However, as you can see, this is a 400-volt battery, so there's big potential there. If you close the contactors and the voltage here is 0, you're going to have discrepancy in the potential. So you're going to have one side that's 400 volts, the other side that's 0 volt. There's going to be a big rush of current, and this is going to damage whatever is on the other side. Everything that's on this side is going to have a huge current going through it, and it's going to be damaged. So for us to be able to close these contactors, we need to basically equalize the voltage on both sides of the circuit. How do we do this? Through a DC-DC converter. So this DC-DC converter is usually connected to the 12-volt battery. this DC-DC converter will take 12 volts and convert it to 400 volts. And once we have 400 volts on both sides of the contactors, then we can close the contactor without having current rushing through to the other side of the circuit. So when they come, when reporters are saying, "Oh, the batteries are empty," it wasn't the 400 volt battery; it was the 12 volt battery that was empty. The reason they are still using regular lead acid battery in electric cars now. So these lead acid battery are very fragile and they're not like lithium ion batteries. So lithium ion batteries are usually more, they don't deplete as fast. So they usually they do deplete, they do lose energy, but it's usually a longer process. It's about 2-3 months for even maybe more, I think, for a lithium ion battery to be depleted. So what's actually happening is the 12 volt lead acid battery is dying, and the guy cannot start, or anyone who's driving cannot start the car, because we're not able to have 400 volts on this side to be able to close the contactor. So the BMS doesn't allow contactor 1 and contactor 2 to close if it doesn't detect that on this side of the circuit there's actually 400 volts. Okay?
Okay, but I have a question.
Yeah, go ahead.
I got that the 12 volt battery is suggested to be lead acid, to be lithium battery, right?
So this is one of the, it's a design criteria that whatever company decides to use. So yeah, they decided to stick with lead acid battery, and this is why what was happening. So those cars that were having those problems are cars that used to have 12 volt lead acid batteries.
Okay, yeah, what I know is that sometimes lead acid batteries have advantages in somewhere over lithium batteries. This function exactly, it is recommended the lead acid battery because it will charge and discharge fastly. So even if it's not about the money, if we are not seeing it economically, lead acid battery will be used in such functions.
Every sort of batteries has its advantages and disadvantages, basically. But yeah, so this is a specific case scenario. So lead acid batteries, it's the same thing that you see. So lithium ion batteries are also susceptible to depletion and to temperature. And I think this case scenario was actually happening at very low temperatures. So I don't know if any of you guys live in the mountains. They say when the temperature drops very low, you're not able to start the car very easily. It's because those lead acid batteries are very susceptible to low temperature. So those, yeah, it's a specific case scenario, but like always, sometimes the reporters don't understand what's actually happening, and they just want to report some stories. Yeah, but just for story for you guys to understand just the architecture. And there is still some companies, some OEMs who still use 12 volt lead acid batteries. Like you said, it has its advantages, but yeah, in this case, it was a disadvantage. Okay.
Okay.
Yeah. Okay. Moving on. So, like I said, this is also something that we test in hardware in the loop. The whole point is we do test that if we don't have 400 volts across this side of the circuit, we have to make sure that the BMS doesn't close the contactor. If the BMS does close the contactors, that means it's doing something wrong, and they have to go back to the software team, tell them you're closing the contactors while still it's not detecting 400 volt on this side. So I have to test this in the HIRRIC. So we don't want basically to test this on an actual battery, where if you don't have 400 volts on this side and you close the contactors, this is going to cause a lot of damage. So again, going back to why hardware in the loop is beneficial and useful. Okay, moving on.
Okay. Yeah.
Moving on. So charging sequence. Who of you guys know how many type of chargers we do have now?
Is it PWM,
Yeah.
MPPT?
Okay. So type of chargers, I mean, so if you go and you want to plug the car, not the functionality, but what is the voltage? Is it DC DC or is it AC DC or okay? So currently on the market here in Europe, UK, we currently have about 3 types of chargers that are available. So wherever you pull your car, these chargers are going to be available. It's going to be either 400 volt DC charger, an 800 volt DC charger, or an AC charger. Okay, either single phase or tri-phase. Now, when you're going to charge your car, you don't know which type of charger you're gonna get. And as a customer, you shouldn't have to worry about these things. It's our job, basically, to make sure that your car does charge whatever type of charger that you're using. And this is also done by the BMS. So you go in, go down from the car, plug it in. Once you plug your car, the BMS software should be able to detect the source. If it is a 400 charge battery, if it is a 400 volt DC charger, if it's an 800 volt DC charger, or it's an AC charger. So as you can see here in this circuit, we have 3 separate circuits. The red one is for 400 volts. So if it detects that the source is 400 volt, it will close contactor 1 and contactor 2. If it detects that the source is 800 volts, it will close contactor 3 and contactor 4. So it will make assuming that you have a 400 volt battery. So this is not standard. It's gonna be dependent on every OEM, on every design, but this is a generic example. So if you have a 400 volt battery, and you're plugging into an 800, you're gonna need in your car a DC-DC converter that converts from 800 to 400, and then you can charge your battery. Or if you plug into an AC source, then we're gonna have contactor 5 and contactor 6 and closing, and we're gonna have an AC-DC converter to be able to charge our battery. And again, this is all done in the BMS, these detections, and it should make sure that in the hair rig, if I do provide it with a 400 volt source, I need to make sure that contactor 2 and contactor 1 are closing. If I do provide it with an 800 volt, I need to check that contactor 3 and contactor 4 are closing. So I need to make sure that these are closing and no other contactor are closing. We don't want to have several contactor closing. So if contactor 3 and contactor 4 closes and then contactor 2 as well, we don't want that. So these are all done in the hair rig and designed by the BMS. I'll go back to the BMS team, tell them your contactor sequence control is wrong. Please fix it if this is not happening. Okay?
Okay.
Another thing, just discussing it, is contactor sequence. So as you've noticed, we have a lot of contactors in an electric car, and we have to make sure that all the contactor sequence are correct. If it's charging, discharging, starting, so this is the start circuit whenever we want to start the car. So all the sequence that needs to be ensured, this is also tested in the hearing. The other thing is the contactor health. So as you know, in some case scenarios, you might have the contactor and the contactor will stuck close. It will be welded due to the amount of current going through the contactor. So if this is the case, we need to be able to detect this. How do we do this? So assuming contactor 1 closes and never opens back because there was welding, a lot of current going through the circuit, and this has led the contactor to be stuck closed. This is a very likely scenario to happen. So we need to detect it, and if it is the case, we need to make sure we never close any other contactor. And again, this is also tested in the hair rig, and this is a functionality that the BMS should be able to perform flawlessly, because we don't want a contactor to be stuck closed and then trying to close other circuits. This is gonna cause blow up of the battery. Okay?
Yes.
Fast charging. Why do you think I chose Tesla for this fast charging? So Teslas usually don't have, are always promoting their fast charging capabilities compared to all the other OEMs or companies. As you might know, fast charging is very unhealthy for the battery. So the more fast charging the battery go through, the worse the lifespan of the battery is going to be, and the worse is going to be able to withstand energy in the long term. So the lifespan of the battery is going to be reduced the more fast charging cycle it goes through. So in the BMS software, we have to make sure that we're counting the fast charging cycles. So every time the customer does a fast charging cycle, we need to record this in the BMS for us to be able to know basically two things. The other one thing is prediction of the lifespan of the battery, and this is also good information when the car comes back for repair. They'll just plug in the car and they'll know how the customer has been treating his batteries, so they will know why there is a problem with the batteries, for example. The other thing is determining what's called state of health and state of charge. Does anyone know what state of health and state of charge is of the battery?
Is it the percentage of the battery?
Perfect.
How much it is full?
Perfect. So the state of charge is basically like every phone. You'll see it 100%, 90%, 80%. Now, the more the battery goes through a fast charging cycle, the model used to predict. So it might be a surprise for you. We cannot actually measure the state of charge. It's a model that predicts the charge state of the battery. So the more fast charging cycle it goes through, we need to record this so that at a later stage we'll be able to better predict the state of charge of the battery. And this is why, if you notice, after having your phone for 2-3 years, it's gonna be the state of charge is gonna be dropping very fast. So this is actually a model because it knows that the battery cannot keep the same state of charge as when it was new. And you might also notice on your phones, when you use a very fast charger, that damages your battery. And it's the same thing in an electric car. Okay? Word? I don't know if someone has anything.
No. Good.
Okay, so state of health is something else, like state of charge. So state of health is basically also used to predict the health of the battery, how much energy it can still store, and how much it's depleted. So usually a battery that's treated well should last between 5 to 10 years. If you always fast charge your battery, if you're treating it also fast charging, fast discharging, all these things, I would say the lifespan of the battery won't go beyond 5 years. And this is also now for your sake, guys. In Lebanon, I know there's a lot of people installing solar panels and charging their batteries and all these things. So you don't want to fast charge your batteries. If you do this, the batteries are not gonna last very long. So just keep that in mind. Okay?
Okay.
Good. Moving on. One scary scenario is thermal runaway, and this is also something that is designed within the BMS software, and I also do tests in hardware in the loop for the OEMs. So how do you think we start detecting thermal runaway in the battery? So thermal runaway is basically when the battery catches fire. So how should we detect thermal runaway using the BMS software? So any ideas?
So is it a sensor that will detect the temperature, then at a specific temperature it will turn off the system?
Perfect, very well. So usually it's the temperature sensor. So if you remember when we started, we spoke about the CSCs. So this is gonna be the same temperature sensor that was used in the CSCs. And how we detect thermal runaway is usually the CSCs are tracking the temperature of the cell. And once there's a sudden increase in the temperature, so thermal runaway is something that happens very fast. So the temperature of the battery will go from, let's say, 60, 70 to 200 all of a sudden. And if this case happens, the thermal runaway is detected by the BMS. Usually, it's very difficult to stop a thermal runaway event. But once it happens, there are two case scenarios that the BMS will go through. First of all, detect if the thermal runaway is limited to one cell. So it might be, if you're lucky, that one cell has caught fire and the fire hasn't propagated to the other cells. If this is the case, then what the BMS should do is will disconnect all the contactors and will basically never connect the battery again. You're gonna need to take the battery to take the car to the dealership and have it serviced basically. And if you're lucky and it's a hybrid, you'll still be able to use the engine, but you're never going to be able to use the batteries again until it's being serviced. Now, the other problem is if the fire propagates from one cell to another and starts to expand. Same procedure. It should start by disconnecting everything, try to isolate some of the cells. Usually, now the new requirements are to be able to contain the fire for, I think, around 3 minutes, and it will be asking the passenger to clear the vehicle because, unfortunately, once thermal runaway happens, it cannot be stopped, and we're gonna basically have to wait for the car to go to burn. It's an unfortunate case, but yeah, if this happens, at least the BMS will try to stop the propagation for at least 3 minutes until the people have evacuated the vehicle. Okay, I think we're gonna be running out of
I have a question.
Yeah, go ahead.
Okay, usually we firefighting the fires using water.
Yeah.
It is not recommended to use water with electricity.
No.
So is it contains like foam type firefighting materials or gases to get out?
There's no way to fight it. There's no way to fight it, unfortunately. The only way to do it now, so all the firefighters now in Europe are required to have a pool, so like a swimming pool. If they reach a car that has caught thermal and electric car, they just grab it and put it inside the pool and wait for it for a week until it has burned down all the cells. There's no way to stop the cells from burning. So just need to contain the fire. So usually they put it in a swimming pool. The problem is batteries have their own oxidants inside and their own fuel. So once it starts, it doesn't need any oxygen from outside to carry on to keep the fire alive. So it's everything contained within it. So the only thing that the firefighters can do is take the car, put it in the pool, and wait for a week or two until the battery has the whole battery pack is burned, basically.
Okay, understood.
Yeah. Okay. So I'm gonna stop asking you guys. I'm gonna finish. I have a couple more slides. We're gonna reach 9:30 in Lebanon time, so Lebanese time. I'm gonna try to go through these slides so we can stay on time. Okay, so another thing that is tested, as you know, nowadays, we don't have only one ECU in a car. So we have up to 20 to 30 ECUs, and every ECU is communicating with other ECUs. So in my hardware in the loop, I have to have a model of all the other ECUs as well. And in testing, I have to make sure that the BMS ECU is communicating with all the other ECUs basically at all time. And in case there's a cut or loss of communication, I need to be able to know, I need the BMS software to, the BMS ECU to flag this to me and tell me, okay, I've lost communication with this specific ECU, and this is a functionality that I would need to test as a hardware in the loop engineer. Okay, other scenarios is crash scenario. So usually you might have a crash at any time, and assuming you do, you're gonna receive a signal from the vehicle ECU, so the main ECU, to the BMS ECU, telling, okay, the car has crashed. So as a safety precaution, the first thing that it's gonna do is gonna disconnect all the contactors just to avoid any, in case there was a penetration to the battery. And the BMS software should continuously monitor all the temperature of all the cells at all time, just to make sure that the battery is safe in case of a crash scenario. Okay. Another thing, like we discussed a bit about the state of charge. So this is usually done in the ECU itself. So the state of charge is done through 3 different techniques nowadays in cars. One of them is current-based method. So this is basically done by monitoring the current going out of the battery and estimating the power left in it, and this is how the state of charge is determined. Another method is voltage-based method, which will be monitoring the voltage of every single cell, and it will be going through this map. So assuming it reads, for example, a voltage of 3.4, the temperature, the outside temperature is, let's say 20, it will return the state of charge accordingly. So it's just a lookup table that is used to predict the state of charge. Okay. And the final one, which is the most complex one, is using observer model or using the model running that will be predicting the state of charge. Okay, another thing that the BMS software should do is basically monitor the temperature. Like we said, it is monitoring the temperature, but it needs to make sure that the temperature doesn't exceed a specific value. So it is going to be doing this by controlling a pump that will allow the coolant to flow through the battery. So to do this, it's gonna be monitoring the inlet temperature of the coolant, the outlet temperature of the coolant, comparing the temperature between the inlet and the outlet to know how much heat we're able to withdraw from the batteries. It's gonna be also monitoring the whole module temperature, individual cell temperature, because even though the whole module temperature might be low, you might have cell in the middle of the path that has very high temperature, and this is not something that we want, because this might cause thermal runaway at a later stage. We need to know the ambient temperature. So if it's very hot outside, we know that we're gonna need to have more coolant going through. If it's cold, that means we can allow less coolant to go through, and while extracting the same amount of heat, and the coolant flow. So the amount of coolant going through the system, and this is also part of the BMS software functionality. And I usually do test this in hardware in the loop as well by simulating temperature cells. I'll say this cell has this specific temperature, and then I'll check if the BMS software is asking for more coolant to go through the system or not. Okay, that's it, guys. I think I have a couple more minutes for questions. Let me stop sharing my screen, and or unless someone has any questions that need to refer to a specific slide, please go ahead.
I want to tell you, thank you. It was so helpful meeting. I'm mechanical student, and I didn't know anything about batteries and electricity before this meeting, and so very helpful. Yes, it's like مثل يعني تعرفت على كتير اشياء اساسيه بالباتريز هيك اشياء.
عنا الميكانيكال انجينيرز نعتبر ايام الكهرباء شيء شعوذه.
يس وبصير متعصبين للميكانيكال، يعني بصير يقول الكتريكال لا احنا ما خصنا فيه.
This is one of my problems that I had, but stepping into this has been very enlightening for me as well, and it's been very interesting. So I'm glad I could make it easier for you to understand some of the electrical concepts. I'm not proficient in electrical engineering, but I think I have improved since I've done my PhD and now with my work as well.
Yes, I said thank you. But I want to ask you a question.
Yeah, go ahead.
You said before you have do an internship in a Caterpillar company in Jalad, in Lebanon. Was this helpful for you in mechanical?
In terms of, yeah, this is something outside. So
yes, I'm asking you that. Sorry for interrupting you. I'm asking you that because I work in a competitor company for Jalad. Okay. Also in Caterpillar, but I don't see that the mechanical, the formulas, the math, the mathematics, the physics that we have learned in university. We don't see and work. We don't see on site.
You're correct. This is يعني أنا أتقول لك صراحة الاكسبيرينس تبعي in this field. You in Lebanon you're mostly a technician. So
yes, like electrician.
Yeah, the only difference is you have the background knowledge of a mechanical engineer, and it's up to you to make the correlation of what you're seeing with what you've learned. So you won't be able to see the content of an engine. You won't be able to see the content of a dyno. You won't be able to see this if you're sitting at home. Now you see it, you need to make sense of it and correlate it to what you've actually learned in university. It is difficult because no one is explaining this, but it was beneficial for me to have it on my CV for one main reason is when you come to a European country or like here in the UK specifically, every engineering student on their third year, they go and work in companies and proper engineering companies. And if you're coming here and you don't have on your CV any internship of any kind, they're not gonna be very impressed with you. So I needed to have this on my CV because when I was applying for my PhD, it's basically like a job. So I needed to have experience on my CV, and it was good for me because I had experience in Lebanon, in Porsche, in Audi, and in Caterpillar, even though it's technician, but it's still experience, and they valued this. And once I was having a discussion with my supervisor, and he told me these are one of the main points that we accepted your application. So they might not be able to explain things. It's up to you're gonna need to put in some extra effort. Ask for if they can share some of the documentations with you. Like at Porsche, I was able to get my hands on some of the documentation, the engineering files of the design. those were very helpful for me. I went through them. I was reading them. Some of the engineering concepts were there. So you're gonna have to make the most out of this. Basically, you're gonna need to try to get. This is what you get in Lebanon. Try to make the best out of it. Unfortunately, this would be my answer.
Okay, فهمت عليك. Yes, it's good for my CV إذا بدي أطلع لبرا أو بدي أسافر من لبنان إنه أنا اشتغلت بهذا الدومين.
Exactly.
Thank you كتير لك.
Merci, thank you. Ward, yeah.
Okay, as you mentioned, using the systems you mentioned, it is easy to control things. It seems we're in a good level with the control things. Why not to make a system like the ones you mentioned to self-drive a car? I hope you understand.
Okay, so just it's a good thing that you felt these things are easy, because they're not. So I tried to simplify things as much as possible. So in the figures,
So it seems you did it.
Exactly. So I've been told that it's gonna be first, second year engineering. So I tried to make things as simple and representative as possible. Now, what's actually happening in the background, there's a lot of things that I didn't go through here. So it is in some sense, if you know what you're doing, it is possible. So companies are working on self-driving cars. The problem is, if you can't drive it in Lebanon, I'm not gonna get inside the car that's self-driving. You can drive a car in the US, in UK, where it's only using a couple of sensors to see where other people abide by the laws, basically, and they don't drive like crazy. As long as it's not able to drive in Lebanon, I don't think I can trust the self-driving car yet.
Okay. Understood.
It's easy to drive on the highway. It's easy to design a car to self-drive on the highway. The problem is to have it drive in India or in Lebanon or any of these where you don't have white lines. So this is one of the inputs to the self-driving. When you have people that are predictable, so we don't have, if there's a sign that says 50 miles per hour, everyone is driving 50 miles per hour, not people just jumping in front of you, some driving 80, some driving 20. So when you limit the inputs, it's easier to design something. The more variables you have, the more difficult it is to have a representative self-driving car.
Okay. I wanna say something. Electrical engineering is more important than mechanical engineering. Okay. The reason is that try to attend this webinar by charging your phone in a mechanical way. Okay, Joseph. No, it's a joke.
I think he's gone. Okay. And anyone else, guys? Yeah. Hanan? Yeah.
Yes, I'd like to thank you for this informative session. It was really appreciated. يعني I learned a lot. كان في شوي غموض عندي أنا من ناحية الباتريز وهيك فكله توضح بهذا السيشن. Thank you so much. I just want to ask about the firefighting technique. أنا بعرف إنه using the CO2 fire extinguisher is the best one for the electronics devices أو electrical parts. ليش ما بيطفوا ليش بيطفوا بالwater instead?
For electric, so it's chemistry basically inside the battery. What's going on? It's chemistry. So for electronics, it's different than for batteries itself. So for batteries, it's the oxidant is inside, so it doesn't need oxygen from outside to burn. The fuel is from inside, from whatever compositions is there. You might be able to put it off with whatever firefighting technique, but it is gonna be turning back on again. So no one has ever proven that you can put off battery pack that's on fire. You just have to wait for it to burn. And once the fuel internally is gone, once all the chemicals are burned, then you'll be sure that the battery is not burning anymore. Unfortunately, this is how they're designed.
Yes, I see. Thank you so much for clarification.
No worries. Good. Okay. Any more questions, guys? I think I'm gonna need to drop off.
Guys, does anyone have any more questions? Okay, I guess we're all good now. I need to thank you so much, Dr. Sessine, for today's presentation. It was very detailed. Thank you so much. And I need to thank you as well for making it very interactive. Really, we really appreciate it. And I want to thank everyone who attended today, and I hope you make the best out of it. Okay, as I mentioned, guys, the recording of this meeting will be posted on our YouTube channel. And you can visit our social media accounts. Ali, can you please send our Linktree link on the chat box? You can visit this link to view our social media accounts, our LinkedIn, our Facebook, our YouTube, and our Instagram. Thank you once more, everyone, for attending. Thank you again, Dr. Sessine, and we hope to see you another time in the future, inshallah.
Thank you. Thank you very much. Merci.
You're welcome.
Bye-bye.
Thank you. Goodbye.
Bye.